The Virtual Atomic and Molecular Data Center (VAMDC) and Europlanet ID's teams developed a database service for laboratory spectroscopy of solids in the domains of planetary science and astrophysics. The Grenoble Astrophysics and Planetology Solid Spectroscopy and Thermodynamics Data Service (GHOST). You will see an example of what can be performed with GHOST through the analysis of Pluto's surface. Pluto is the first observed trans-Neptunian object. Discovered in 1930 by the astronomer Klein Tombaugh, Pluto used to be considered as the ninth planet of the solar system. However, between 1990 and 2006, discovery of celestial objects similar to Pluto beyond Neptune's orbit disrupted the definition of a planet. Since August 2006, the International Astronomical Union has classified Pluto as a dwarf planet. Pluto's surface is known to be composed of solid methane, CH4, dinitrogen, N2, and carbon monoxide, CO. It contains what we call dark material as well. Moreover, temperatures on Pluto's surface are very low, between 30 and 70 kelvins. The NASA mission, New Horizons, will be in 2015 the first to perform a flyby of Pluto. We would like to analyze a new hemispheric spectrum of Pluto ranging from 1 micrometer to 2.5 micrometers, corresponding to the near-infrared region, in order to find out which molecules are present at Pluto's surface and in which state, pure, diluted, mixed, etc. Two unidentified weak bands are observed around 1.690 micrometers and 2.225 micrometers. The research of the origin of the first one will help us learn more about Pluto's surface. Firstly, we'll focus on CH4 and look for corresponding data relevant to Pluto. On GHOST webpage, we select Search in the menu bar and Advance. We indicate the species formula of interest, CH4, and we see it in the upper right corner of the webpage that 24 products are found. By clicking on View Results, the answer of our query is displayed at the bottom of the page. We can see the results in two blocks, spectrum and band list. There are four types of products: optical constants, absorption coefficients, transmission spectra, and band list, but also different spectral ranges, different states of CH4, some mixed with other molecules in various phases and various temperatures. Actually, we are searching for some pure CH4 in the near-infrared spectral domain and in the relevant temperature range, 30 to 70 kelvins. Thus, we move up back to the form and fill the options of interest. In the constituent compound state zone, we indicate pure. We add the temperature range, and the spectral range we choose extends from 1 micrometer up to 2.5 micrometers. We click on View Results and we see that 8 products are found. We would like to look at the 40K absorption coefficient spectrum. We click on the small table located in the line of the corresponding product with ID 519 to display the spectrum and associated information. On the spectrum, the abscissa unit is centimeter minus 1, so we change it to micrometer in settings unit. We zoom to the spectral range where we have observed the unidentified band on Pluto's spectrum, and we can see this band at 1.689 micrometers. We keep the spectrum in the shopping basket by clicking on Export this spectrum in order to use it later. Now, we intend to verify the exact position of the 1.689 micrometers band if it is really due to CH4 and not to an impurity in the spectrum, and we'll try to determine which vibration mode it corresponds to. In the advanced search form, the previous settings are saved. We click on View Result. We will look at band list information corresponding to the sample temperatures at 30K. We click on the small table associated with ID 37. Then we click on the Bands tab. We find a band which corresponds to about 1.689 micrometers. We click on the small table associated and we can read the accuracy of band position at position peak accuracy, namely 1 centimeter minus 1. If we look at transition assignment, we can read nu1 plus nu3 vibration mode. The band is identified as CH4 and assigned as the nu1 plus nu3 combination of vibration modes of the main isotope 12CH4. We are able now to complete Pluto's spectrum with these information. We would like to compare our ghost spectrum with the spectrum of Pluto. To do that, we go to the export page and select spectrum and adjust the download options, in particular the spectral range of interest for this spectrum. A folder containing the spectrum and associated information files is loaded on the computer. The ASCII file contains wavelengths and associated intensities for the present spectrum. Using this file, we can plot all together the pure CH4 spectrum and Pluto's spectrum and obtain the present figures. We can notice on these figures that most of pure CH4 bands are shifted in Pluto's spectrum. One possible reason is that CH4 on Pluto's surface is diluted in N2 ice. Thus, secondly, we'll search for N2 data relevant for Pluto. We go to the advanced search page and reset the form. We fill the species name with dinitrogen. We want pure dinitrogen in the temperature range of 30 to 70 K and in the spectral range of 1 to 2.5 micrometers. We click on View Results and we see that only optical constants are available. There are two phases of N2 in the available data: alpha at 33K and 35K, and beta at 36.5K and higher. In order to determine which phases is better adapt to our spectrum of Pluto, we are going to compare the width of the N2 band around 2.15 micrometers on Pluto's spectrum with spectrum corresponding to each phase of N2 data. Let us start with N2 alpha phase data at 35K. After changing the unit to micrometer, we zoom on the band of interest. We note the real position of the band and the positions of the left and right phase, which are respectively 2.148 micrometers, 2.1476 micrometers, and 2.1487 micrometers. The corresponding width is about 0.0011 micrometers. We do the same work with N2 beta phase data at 38K. We measure the position of the band 2.1485. On Pluto's spectrum, the band is located at 2.148 plus or minus 0.001 micrometers, so it is not possible to discriminate the phases on the basis of the band position. Though the width equals 0.09 micrometers, and this value is closer to that of the band on the beta phase data, namely 0.1 micrometers. Now that we have identified a beta phase as N2 data phase relevant to our study, we will look for CH4 mixed in N2 in the near infrared in the 30-70K temperature range. We reset the advanced search form. We fill species name with methane, constituent compound state with solid solution, and spectrum type with optical constant. Then we click on View Results. There are data in beta N2 at 36.5, 38, 41, and 43K mixed by some way with CH4 and CO2. We choose to display the spectrum at 38K. We zoom on 1.6-1.8 micrometers range, and we observe that the band around 1.69 has disappeared. This band is a witness of the phase of CH4. It is present only for pure CH4. Let us now compare the sample spectrum with our Pluto spectrum. We download the spectrum file like it has been done previously in the pure CH4 spectrum. Once the spectrum file is loaded, we can plot Pluto's spectrum and the two loaded spectra on the same figure. On the figures, we can notice clear spectral band shifts between pure CH4 and CH4 diluted in N2 laboratory data. Pluto's spectrum has the pure CH4 1.69 micrometers band, but it has an intermediate position for the other bands, which means that pure CH4 and also CH4 diluted in N2 ice are present on Pluto's surface. We want to know the composition of the studied sample. We click on More Details at the bottom left of the web page. In comments, we can read that these data have been compiled from a series of samples of beta N2 with different low CH4 concentration from 0.1% to 2%. We click on the small table below corresponding to ID 161. Then we click on small table of the materials table below with ID 476 and on the small table of the constituents table below with ID 285. Now we get the information on the state of the solid in State Phase Name rubric and on the molecule composition of the Table of Species Organization rubric. Actually, CH4 and N2 are in solid solution and CO2 is just an impurity at few parts per million level. If we click on Small Table of CH4, we can read a lot of fundamental data on the CH4 molecule, namely chemical structure and composition, isotopic composition, spin isomers, fundamental vibration modes of the free molecule, and a series of general and specialized web links. Finally, we see in this demonstration that it is possible to make spectral analysis and study of the composition of Pluto's surface in a simple way using GHOST facilities. This demonstration is made with the current beta version of GHOST. GHOST version 1.0 will be released before the end of the year, with many improved functions and much more data on the various solids, ices, minerals, organics, meteorites, etc. Thank you for your attention.